Not trying to do too much extra
Six,
here.
7. Video 7.
Well, you got to put the 5 up. And
Well,
I got
this is-
2.
Oh, this is the sign for 7.
But that's 3 and 2.
That's 3.
We're wasting time and we can't do
Oh,
that
that's
in
right.
this
Let's go. Le Chatelier. This one's actually a very important topic.
video.
Slightly complicated.
But really not. The
Not
way
too
that
bad.
we teach it,
Not too bad.
AATT, you'll see it's
Yep.
very simple.
So you might have to pause and write this down. All it's just saying is that
Mhm.
if dynamic equilibrium can be shifted by doing a few different things, adding reactants, adding products, taking them away,
Right.
adding heat, because heat's in there, changing the pressure. If we do any of that,
Bottom line, you can manipulate an equilibrium by doing the following. We're going to teach you how it changes when you manipulate it.
right. And so this guy's credited, Le Chatelier. Was he French?
Sounds like it.
Sounds like it to me.
Mhm.
You always know these things.
His statement is that simply an equilibrium is going to shift depending on the stress that we, the humans, put on the system.
Yep.
To reestablish that equilibrium if it's possible.
So that's one of the cool things about equilibriums is once they get there, they actually want to stay there.
Right. Because the reverse and forward reaction want to be in this kind of dynamic state of forward and backward, backward, forward, backward.
So
forward.
simply, these are some things we can do to stress it. We can add or remove products or reactants.
Right. So like if I put more ingredients into my reaction,
You can make more cookies.
right. If I decrease or increase the temperature,
You can change the reaction
and if I can decrease or increase the pressure, I can change the reaction.
based on gases only.
And these are all really related back to collision theory,
They
which
really
is the
are.
underlying reason why a reaction forward or reverse happens in the first place.
Okay. Now here's the actual rules. I want to get through these rules so we can practice them.
Right.
So the rule AA, first of all, the rule is AATT.
Right.
We're going to get into AA right now. AA is all equilibrium shift
Away
from
from
the
whatever
chemical.
you add.
So that means I shift away. Notice I got the A's repeated. So that away from what I add is if I'm adding a reactant, it shifts away from the reactant side towards the product side. If I add a product, it shifts away from the product side towards the reactant side. I want to make sure we're clear there.
AA, shift away from what you add. TT, toward whatever we take. Okay, so if I remove something, the reaction equilibrium is going to shift to replace what you took away.
Exactly.
Okay, and that is why we say toward what is taken.
Right. So if you take a reactant, it shifts backwards towards the reactants.
To replace what got taken away.
And if you take one of the products because you like that product you're making, you can force the reaction to
make more product.
It's sweet.
Exactly.
Isn't that how that works?
Mhm. So different stresses, concentration. Obviously, you change a concentration, the rate of reaction is going to change.
Mhm.
Therefore, adding a chemical will shift an equilibrium according to those AATT rules.
Yeah, I mean, if I'm adding more of stuff, I'm increasing its concentration. So that's where that comes in.
More collisions, more reactions, shift
Right.
away from what you make.
Now, temperature, if I increase or decrease temperature, I'm either increasing the movement for more collisions or decreasing the movement for more collisions. But normally you're going to see the temperature in kilojoules written as a product or a reactant.
Right.
And we're just going to treat them like that to make this easier.
Because some reactions are endothermic. And if it's not endothermic, it's exothermic. So heat plays a role. It's an ingredient in the reaction.
Yes,
The particles can't collide with the right enough energy if they don't have the right heat.
Right.
Pressure only works for gases. And so if you increase or decrease the pressure, it's going to do the following things. Increasing pressure,
pushing.
forces the gas particles together. They'll react more as a result because they'll hit each other more. And the shift will shift towards the side of the reaction that has fewer moles of gas.
Right. And that's the coefficients in front. And it makes sense because there's less room. You push like this, less room. So less room, less moles. That's
Right.
where I'm going.
If I decrease the pressure, those gaseous reactants are going to want to stay far apart. And they'll actually fall apart sometimes and shift towards the side with more moles of gas because low pressure is favoring ideal gas behavior.
And then the direction of an equilibrium can be shifted by stressing the system as described.
Yep.
AATT and the amounts of reactants and products will change based on the stress induced
Yep.
or introduced. Once this equilibrium is reestablished, again, concentrations become constant. The rates of the forward and reverse reaction again
Become equal. So when you put a stress on an equilibrium, it changes for a moment or two, and then it chills out again.
Right.
And that's when the rates become equal. So I'll do the first one, then you do the second.
Okay, cool.
Changing some concentration.
Okay, so what I'm going to actually want to do is just figure out where these things are. So if I'm going to add H2O, I see there's my H2O. I'm going to add H2O. I go, the saying says AATT. I go away from what I add, so I will shift to the left. See how we did that? And notice the notations he's putting up top. That's what helps. So now the concentration of ammonia will go up. So that's something we didn't talk about necessarily in the notes. If I shift to the reactant side, every reactant goes up. If I shift towards the product side, the concentration of all the product sides go up. Does that make sense? So let's do the next one. I'm going to add oxygen. I see oxygen is on the reactant side. So if I add oxygen, I go away from what I add. So that means I have to go away from the reactant side to the product side. Now everything on the product side goes up. And the question says, what happens to NO? And guess what? That just so happens to be a product. If I'm shifting that way, it must go up because it's a product. Good?
Yep.
Okay, now I'm going to add water again, which we did in the first one. So when I add, I go away from what I add. I added a product, so I will go towards the reactants. Okay, so I'll go to the left. But it says now what will happen to the concentration of NO? Well, NO is on the product side. So if I'm shifting to the reactants, my product side goes down. That makes sense.
Yeah.
Okay, and if we now the next one is add NO. Well, that's the one we just saw go down. So these are product side. I go away from what I add, so I will have to shift to the left. And if I shift to the left, and I'm still not convinced that's on your left, but maybe it is. Is this on your left? Tell me tomorrow.
It is.
Left. Yeah. And then which concentrations will decrease? If I'm shifting left, everything on the right will go down. So the heat, the NO, and the H2O. And now this is legitimate. Even though I add the NO, that's only for the instantaneous that I add. After the reaction goes, the concentration of the NO will also decrease as it's being used to make more of those reactants.
Mm-hmm.
Good? Good. All right, my turn. Tag in.
Woo! All right. So let me get the clicker. Oh, wait, you don't need the clicker. I should just talk. Okay. Heat is now part of the reaction. In this case, the heat's a product. So if we add more heat, that means we're going to increase the concentration of heat. It's like we're adding heat. That goes up. Which direction would the equilibrium shift?
To the
We're
left.
shift away from what we add. So that's to the left. Which concentrations would decrease?
So then everything on this side,
Is going to decrease because it gets used up. Which concentrations would increase? Well, anything on the side that the big shift arrow points towards would increase. Because if I add more heat, I can break down or combine nitrous oxide and water more often to make more oxygens and ammonias. So that's what would happen.
good.
Lots of practice. You got the next one while you're there? Cool, we're on a roll. I got to click a button though. There we go. Pressure's on a gas. So remember, ideal gas laws are kind of being observed here. So if we increase the pressure, which direction will the equilibrium shift? It's a gas. If we increase the pressure on a gas,
I'm gonna go.
it's going to away
Yep.
because it's going to get squeezed into the water.
Yeah, sometimes you have to use a little bit of reason and logic on that.
Mostly reason and logic here.
So I'm gonna shift to the right.
What will happen to the concentration of the aqueous carbon dioxide? Well, we've
if I'm
shifted.
going this way.
to
This
the
stuff
right.
has got to go up.
The concentration of CO2 is going to go up.
Oops.
If the pressure is increased, the direction of the equilibrium will shift to the right again.
Okay, we just did that.
But what will happen to the concentration of the CO2 gas?
Oh, this is on the reactant side. So if I'm shifting away from the reactants, that will go down.
Just look at where your equilibrium shift arrow is pointing to. Whatever it's pointing to gets more. What's pointing away from gets less.
Okay.
Now, if the pressure is decreased, so we're going to remove the pressure on the system.
So
We're
now
going
I'm
to
gonna go
favor
gas.
the formation of a gas under
So
the
now we'll go
ideal
left.
gas law. So we're going to shift to the left. What will happen to the concentration of the aqueous CO2? It's going to drop. Our equilibrium shift arrow is pointing away from the aqueous CO2, so it drops. And if we decrease the pressure again, we're going to shift to the left, and the equilibrium will favor the formation of more CO2 gases. That's it.
We did
Press the button. Press the button.